So hi everyone. So I'm going to be talking a bit today about track reconstruction algorithms in high pileup environments. And as I go through the talk, I'll kind of explain a bit how I'm interpreting this title, which is perhaps a little bit in a hoots. Uh-oh. No, I've lost my, no, it's all right. There we go. Okay, so actually this slide hasn't yet been shown today. So I did want to show it at least once to remind everybody that it's not just software. There are actually detectors behind here. And this actually, the reason I'm really showing it is it becomes particularly important once you talk about something like tracking, where you do need to keep in mind what is the underlying detector components. So here's all four of the LHC experiments. But of course, as I'm going to focus here on high pileup, I'm mostly going to talk about Atlas and CMS. And in terms of the tracking detectors, CMS, for example, has an all-silicon option. And actually, I had to make this plot by hand, if anyone from CMS looks at this very carefully, because I actually wanted to overlay their new pixel detector with the rest of the detector. And as far as I can tell, there isn't a compound one that I found just yet. But I'd love to know where it is. And Atlas, on the other hand, we have two subdetectors in terms of silicon. And then we have this transition radiation tracker, which is a straw tubes filled with gas. I wish I had time to talk a bit more about LHCb, because the geometry makes this a particularly interesting one in terms of algorithms, but sadly I don't. And then of course Alice has to deal with not really high pileup, but certainly in terms of high track density, for example in the TPC. And so there are very many interesting things that one could say about that. But just to get started, I wanted to start with an event. And this is, of course, a Higgs to ZZ candidate event. And the tracks that we're after here, if you want to think about it in terms of physics, are these four muons, which are there in red. Now, another thing I'm not really going to focus on today very much is about how to track things like muons, because when you compare to the pions, that's actually a much easier task. Of course, it's easier only in quotes, because you actually really do need to reconstruct these very precisely. And so these I won't talk about, but what I'm actually going to focus on are these orange tracks, which are all the different pions that one sees throughout the event. For those who might not necessarily be track reconstruction experts, I just wanted to define a few things. So when we talk about track reconstruction algorithms, they can be loosely separated into two parts. So the first part is what we call the pattern recognition. And for those who are machine learning experts in the audience, this is perhaps a little bit of a misnomer. What we're talking about pattern here is not quite what's always used there. And then secondly, the track fitting. So in terms of the pattern recognition, what we're trying to do there is to really identify the energy deposits that came from the particle going through the detector and to say, you know, these ones came from one particle. And the second part, the track fitting, is really to estimate as accurately as possible the parameters of the track. And of course, here we have, you know, the two beams from the LHC gliding somewhere in the center, producing particles. We're going through a magnetic field, and we need this helical trajectory to be able to actually estimate the momentum from the curvature. And then this is, for example, what we use in Atlas in terms of the track parameters. You need 5, you need 2, which really tell you the distance from where the interaction happened, 2 angles, and then a measure of the curvature and or the momentum. Now, one thing, this is a bit of a traditional view, perhaps, of track finding and fitting. In reality, the two actually become intertwined. It's not really the case that first you find all the hits, then you determine the parameters. In fact, as you go along, you need to determine the parameters, because that actually helps you find the tracks better. And as things have become more complex, the two have become really interlinked. So you shouldn't really think of it as two separate steps. Now, here's what it can look like if you look sort of at a typical 13 TV collision. This is looking at Atlas, sort of in, as you slice through. If you look longitudinally here, you actually see all the different vertices that you get from the LHC. And so here's a cartoon version of the LHC, where you have all the different bunches, because of course we have something on the order of 10 to 11 protons per bunch. And we do this to maximize the number of interactions so that we're actually able to do as much physics as we can do possible. So that's good. But of course what actually happens is that typically we have more than one pair of protons colliding at a time. And in fact, here is a plot where it's going to have mu, which is actually going to be something I talk a lot about in the talk, which is simply the number of interactions. This is from 2016. You can see that our average actually started to get up to somewhere around 40. I remind you that our detectors were actually designed for something much closer to 20. And so we're going well beyond the capabilities of what we originally intended to do. But the good side is this means we get to do a lot more physics a lot more quickly. And so that's actually what a high pileup collision can look like. And here again, you're looking in the z direction. And all these little dots here, these are actually the reconstructed vertices, really trying to identify all the different collisions. And this example from CMS is actually got 86 reconstructed vertices. And so you can really see the sort of longitudinal profile of how these interactions happen. Now, of course, experts in the room would start smiling because once you get to this number, of course, not all of them are real. They can be fakes. And of course, this is also a problem in the tracks themselves. We need to worry about the efficiency. We also need to worry about the fake rate. And so here is a little summary of how things have kind of evolved. So we started out in run 1, somewhere around 20, maybe 280 tracks per event. You can count these in various different ways. And then as you sort of change the amount of pileup, you also change some of the beam parameters and the energy. And that's why these things don't just scale linearly. You can get up to something like 600 tracks per event. But when we start looking into the future, we're talking about 7,000 to 10,000 tracks. Or even if you want to go into the hypothetical future, we're talking about 100,000 tracks. And so while we already have a challenging situation now, it's actually going to get even more difficult as we get into the future. And so that's why I think it's an important problem. So what we want to do is we want to reconstruct the charged particles with very high efficiency. And that's actually something that's important because many of the algorithmic solutions that get considered, it's very easy to get a good fraction of the tracks. But where the challenge actually comes in is getting that last final bit of the efficiency, which is actually what we need. At the same time, you need to have a very low fake rate, which is typically below 1%. Now, if you look carefully at the plots, which I show you, you'll actually see different numbers. And this is because exactly how you quote these numbers and how you compare them really does depend on your definitions. But we can discuss that in the questions if needed. Now, loosely speaking, the amount of computing time that it takes will scale in quadrature with the number of tracks or with mu. And so that's why you end up with this highly nonlinear behavior. And so what this means is that it's really very challenging to obtain good performance within our computing resources. And so it's a continual ongoing effort to really optimize and to really get things to go as quickly as possible. And here's an example from Atlas. These are various different software releases that we had during a really large re-optimization where we were able to decrease the amount of time we needed by a factor of 4. Now that sounds pretty impressive. And the interesting thing is that it was actually largely technical changes that allowed us to achieve this. It was not that we came up with some new algorithm to reconstruct tracks. It was actually much lower down. But in the end, you can see it was really important and would have been very challenging had we not done that. Now, track reconstruction is not just about reconstructing charged particles. They're actually used in basically every element of reconstruction and hence physics. Luckily, I don't need to tell you what a jet is. Ben gave a nice little introduction in his talk. However, in all the objects that you think about, things like leptons, primary vertices, even pileup removal for jets and missing energy, and flavor tagging, each of these are actually using tracks. And so if you don't actually efficiently reconstruct them, and not just the ones from the hard scatter, also those from the pileup, then you actually have an immediate degradation in terms of the performance. So now I want to sketch a little bit about how we do it. And so I want to start with Atlas as an example. And so here you're seeing a picture, again, slicing through Atlas, where you see the silicon detectors and the transition radiation tracker. And if you want to think about sort of the pattern part of it, you can kind of think about 5 different steps. So to begin with, what you need to do is to actually take the raw readout that you get from the detectors and form them into 3-dimensional space points. Now here, there's some technology-dependent implementations. For example, when you have a strip, you actually need to combine 2 strips to actually get really your measurement point. And this will also, you end up having very different resolution. Then what you do is you try to group together these space points in order to find a seed for your tracks. And these are meant to be, typically they're 3, and so they're these blue circles that you can see on the sketch. After that, you need to extend them to find additional hits as part of the track finding. Then you come to something called ambiguity solving, which I'll come back to a little bit later, where you really try to resolve between the multiple candidates that you actually have per track. Then finally, and this one of course is just for Atlas, you can actually try and extend into the TRT. Now one thing you might have noticed as I was explaining this is we're talking about going from the center out. You might imagine that we'd actually do better going from the outside in. Indeed, we try this and we play with it. But for Atlas, it actually turns out to be better to do it this way around, except in the specific case where you're looking for particles that are produced displaced from the interaction point. Now, a key part of track finding and fitting is the Kalman filter, which was actually initially developed to track missiles. Of course, now we use it basically everywhere in HEP. And effectively what this is doing is to be a progressive least square estimation, which is roughly speaking equivalent to a chi-squared fit. This is if you run it with a smoother. And there's a sketch here which has actually got a number of different arrows, which is really trying to show you how you start with your measurement point, you move on to the next point, how you estimate your parameters, and then you update with them. And this is exactly how we do it. And this is basically used in many of the different applications because it's very powerful to do things. Now, in terms of Atlas, one thing I mentioned is this ambiguity solver, and I want to spend a little bit more time talking about it here because it's kind of a key feature of the strategy. The idea of it is that we are able to obtain the high efficiency by applying very loose requirements on the tracks during reconstruction. So what you're saying is, I don't care if I get a few fakes, but I want to make absolutely sure that I get every single track candidate that I possibly could. And then you apply an extra step in the process to actually choose which are the best candidates, and you throw out all the rest. Obviously, this is going to take more CPU time because you need to consider all these different track candidates, but it's also the way to make sure that you don't actually miss some of the important candidates. And the way you do this is you define a scoring function. And that, we went the wrong way. This one is plotted over here. So this is actually really our score from the ambiguity solver as a function of the track PT. And essentially, the variables that you use to define it are things like the hit content, whether there are any missing hits on the track, whether they're shared between others, and you actually choose the best tracks, and then you keep going down until you've actually used up all your hits and assigned them to tracks. Now, Atlas and CMS do very similar things, but one thing that is a little bit different, and it's maybe just a bit philosophical, but it ends up being different in implementation, is the fact that Atlas tries to have everything very loose and to do it all in one pass to get the tracks. Whereas what CMS do is they try to find the best tracks first, and then to come back with another iteration of the algorithm, and to keep doing that until you've actually found all the tracks. And this is a plot, and this is showing the tracking efficiency as a function of PT. And all the different colors are essentially all the different algorithmic passes that are run by CMS. I think there are about 9, but maybe I didn't count very carefully. I can count now, but it's probably better not to. So at the top here is a bit of a cartoon illustrating this. So you imagine here that you have the detector with the following hit pattern. What you try and do is you find the easiest track you can find, fit the track, remove the hits, then you have your leftover hits, and you find the next ones. And the idea is that as you clean things out, here you're actually able to access some of the tracks that would have been very difficult to find during the first pass. Now one comment, if you were paying very careful attention, you'll notice the efficiency here is about 0.9. When I said at the beginning we need to get 99% efficiency. The reason for this is that 99% number is for a particle that actually passes all the way through the detector. And the difference here is the particles that you lose when they actually interact with the detector material. So now that you look at the efficiency, you can actually start looking at it as a function of pileup. And so this PU is actually the same as the mu that I defined. And you start out in blue, and you see as you increase the pileup to something even as high as 70, you can see that this has some impact on the efficiency and also some impact on the fake rate, particularly either in the very low PT region or the very high PT region. And there are different effects that are actually responsible for what happens in those two places. Now, just like I was talking about how Atlas spent a lot of time speeding up the reconstruction, CMS actually did an optimization to improve the algorithm at high pileup. And here again, you can see the efficiency using the 2016 algorithm and the 2017 algorithm. And you can see that they got a significant improvement in the efficiency as well as being able to reduce the fake rate. So now here's where I'm going to interpret things a little bit loosely. because I've been talking about pileup, but actually if you look into tracking at the LHC, when you go inside a core of a jet, you actually end up in a much denser environment than any of this pileup, because the pileup is typically distributed throughout the detector. And it's actually there where we see already the limitations of our algorithms. And so this is a little sketch. This is showing you what happens. So when we talked about the space point formation, where you actually take the detector information and you need to really determine the clusters, what can happen is you can end up with the tracks actually so close that they've overlapped. And so you naively just sum up these energy deposits, you get one single cluster. And so before you've even tried to start your track finding, you've already lost the information of where the different tracks go. And this is a plot, for example, where you do it as a function of the PT of the jet, and you just compare the separation between two particles. You actually find that quite quickly you end up getting within a single pixel, first in the longitudinal direction, and then in the transverse direction. You can compare this to the size that we have of the pixels. So this is a problem that we spent quite a bit of time working on. And the first thing that was done was to actually use multivariate techniques, actually a neural network, in fact 7 neural networks, to use the information that you have in the charge deposited in the detector to be able to identify the case where you actually had two merged clusters and then split them into one. And you can actually see this in plotting the resolution. You've actually managed to resolve these overlapping clusters by using that information. Then the second step that we did is to actually know this information, to know the probability that a track was shared, but not actually taken as decision until that ambiguity solver. And when you do that, what you can actually do is really improve your efficiency, particularly at high PT, and this is a tau simply because you get tracks very close by using that information. And this is the example from Atlas, but there have also been very similar techniques and ideas used in CMS. So now looking a bit towards the future, as far as I know, and I'd love to be corrected if I'm wrong, is that our algorithms seem to scale on the order of n squared. And I don't believe there's actually a formal proof saying that this is how they have to be. And of course, we're going to be increasing pileup as we end up going to the future. Now, the other thing that's happening is that computing architectures are really changing rapidly. And we're going to hear many talks in this conference about parallelism, about balance, between CPU requirements and memory, I/O rate versus CPU. And what this actually means in terms of tracking is that we really do need to rethink the algorithms that we're using. The reason for this is that the current algorithms I've been describing are not trivially ported to parallel architectures. I mean, what I was trying to show to you is that you really get the optimal performance by considering the event as a whole, because you have these tracks which need to share hits. You can't just send one to one node, send the other to the other, because you're losing that information about the interplay between your different track candidates. And so this is, of course, something that's being very actively worked on at the moment. And I saw there were some interesting talks in the parallel sessions about this. So some of it can be, for example, trying to define appropriate regions of interest, which you can use without performance loss. And another thing that's quite tricky is if you think about those jets compared to the event as a whole, you have certain regions where there's a lot of activity, and you have other regions which are completely empty. And so you need to think about spread balancing, because otherwise you're going to spend the same amount of time reconstructing that one region of interest in the jet as for the rest of the event. So I just wanted to give you a couple examples. This is a slide I stole, which is trying to explain the idea of cellular automatons, where you can actually essentially use this to really do very rapid track finding, and also it's very naturally parallelizable. And this plot here, which I hope you can see, is actually showing that this has already been implemented in CMS, and they were able to obtain comparable performance with this to what they had before, but to be able to parallelize things a lot more easily. Now, another thing that's been discussed in various contexts is trying to use associative memory, where you can store the possible track patterns directly in hardware. And this means you have your hit pattern, you get your track pretty much immediately. And this avoids many of these arguments about scaling with combinatorics and things like that. The downside is that you can be sensitive to detector conditions, which might actually impact those patterns. Now, there was a prototype that was actually in CDF, and it's currently being installed within Atlas as our FDK, which is our fast-track trigger. And this is a picture trying to sort of show you how you might end up getting these patterns out of your hits. But although it's been discussed, it's not at the moment clear exactly how you could use something like this within offline reconstruction. It's really to do with how would you actually get the data there, how would you get it back, and would that actually take more time than using the algorithms that you had. But nonetheless, something interesting to think about. Now, I only have one slide on this, but there's actually a lot of activity ongoing, and I think there's one talk maybe this afternoon, maybe tomorrow, because many techniques from machine learning are currently being explored in the context of track reconstruction. One example here, and this is, again, this is trying to show you as you look sort of moving out in the detector, you actually have a seed here, and you have a track there. And the idea is that you take the seed, you take the hits, and you really try to predict based on the seed of the hit. And you can use various different techniques for this. For example, LSTM, convolutional neural network. You can include noise. And this actually works quite well, but these are still at the sort of early stages of development. And so, as I was mentioning earlier, it's very easy to get the first bit, well, not very easy, but it's moderately easy to get the first part of the efficiency. The really hard part is getting all the way to the full efficiency. But nonetheless, these are very interesting techniques. So I think I was perhaps a bit hungry, so I got to the end of my talk faster than I meant. But I hope I managed to give you a flavor about how we've developed precise and efficient track reconstruction algorithms, and these are being currently used in the HiPilot LHC environment. They play a central role in track reconstruction, but they demand significant computing resources. There are many challenges that are coming: 50 times more data, order of magnitude increase in the number of tracks, and the sort of smaller increase in CPU power if you really try and control for everything. And so that's the reason why many ideas are currently being actively explored. Things like algorithms to exploit parallelization, techniques from machine learning, and I think that any other ideas are extremely welcome. Thank you.
You are talking essentially about CMS and Atlas, and it is LHCb which is crucially dependent from the tracking. And actually, they did a great job in high efficiency tracking. The question is, in which way do you reuse the experience obtained from other experiments?
Which, I missed one crucial word, reuse?
Reuse.
Reuse. So just to say, I mean, I absolutely did not mean that what LHCb has done is not interesting. It was simply trying to restrict the scope. And it's true because you're looking in the forward region, right? There is indeed high densities. But there are actually a lot of ideas at the moment about how to really reuse things. So for example, there's a software project ongoing to essentially take the Atlas track reconstruction, to remove all the Atlas specific parts, and to make this publicly available. As far as I understand at the moment, the track fitter is available, and then the pattern recognition is in development. And I think that in general terms, if we can find ways to do this in many contexts, that will mean that one can actually share algorithms between experiments. And I think that's very important because, you know, if someone solved one problem, there's absolutely no purpose in trying to have someone try and solve it again from scratch. Sorry?
Probably the other way around, because all that machine learning ideas, are implemented in LHCb since years. So probably, my question more, sharing the experience into big experiments like CMS and Atlas.
No, sure, I understand. I just happened to come from Atlas. That's why I gave you the example. But I think there are also other forums. For example, there is this new forum at the LHC, which is meant to have common discussions between experiments, and I think those are the sort of contexts where such discussions should happen. I think everyone's interested to learn from each other. I think in the middle.
We are actually developing a library for including the CMS seeding, extrapolating the CMS seeding, and it will go inside the ACTS software. So everybody, a library was developed also because your LHCb colleagues asked for specifically the cellular automaton seeding. So this is how we collaborate. So this project is taken by the HEP Software Foundation. And if you want to collaborate, you can just make a pull request. We are waiting.
Sorry, behind you. I think Axel had a question.
So in the past, when people were designing detectors, the idea was basically to make it such that we get good, tracking precision that allows us to get good physics out. But now we are seeing more and more that actually what's limiting is not so much the detector precision, but it's to a large extent also how much can we do in the few seconds we have per event. So do you think that we actually need to invest some brain power on coming up with ideas to improve detector layout, tracking detector layout, that also takes that dimension into account, say when going to the FCC or whatever?
So I think the answer is yes, and I think we're actually trying to do that already now. So taking again the example of Atlas and CMS, we're working right now on our phase 2 upgrades, and this is really being done in an integrated way with the reconstruction algorithms themselves. So really trying to say, not just can we get the best precision on a hit, but really how do we use that precision to really get the best track out, for example. And so this is certainly what we're trying to do. It's not easy because connecting all these things together can be quite difficult, but I think we're really trying to do that now. And I think that's important because I don't know if I really showed it, but some of this was a surprise. For example, like how much we could do inside these jets to actually be able to split them. This was not something people thought, single track resolution, it's finished. It actually turned out that's not necessarily the case. So I think there is a lot of connection between all these things, and I think it's very important to do this.